On a windy day in New York or Toronto, you can stand under a glass tower and hear it creak just a little. Not because it's weak, but because it's alive, moving with the wind, designed to bend, not break. Now picture another building, the Pantheon in Rome. It has been standing for nearly 2,000 years. Same planet, same rain, same gravity. So why does one feel temporary and the other feels forever? Most people hear this and think the answer is simple. Roman concrete was magic. And yes, Roman concrete is special. But that's not the full story. The real secret is bigger, and it's a little uncomfortable, because it says modern buildings don't fail just from physics. They also fail from choices, budgets, speed, and what we reward as a society. And here's the twist we're going to chase. Many modern skyscrapers are not built to last 2,000 years. They're built to meet today's codes, today's business plans, and today's timelines. Romans often built for power, pride, and worship, things meant to outlive a lifetime. That difference changes everything. Before we crown Rome as the champion of durability, we need to be honest. Most Roman buildings did not survive. Fires, earthquakes, wars, and simple neglect erased a lot. What we see today is the survivor set, the strongest, the luckiest, and the most cared for. Also, the best-known survivors often had a huge advantage. People kept using them. The Pantheon, for example, was turned into a church centuries ago, which helped protect it. A building that stays useful gets repaired. A building that goes empty often dies. So the mystery isn't why every Roman building lasted. The real question is, why did some Roman structures last so long, and why do so many modern ones get replaced so fast? Keep that question in your pocket. We'll answer it piece by piece. Concrete is basically three things mixed together: a binder that glues, water that starts the reaction, and rocks or rubble that give bulk. Today, the binder is usually Portland cement. Romans often used lime plus volcanic ash, called pozzolana, which can harden even in wet places. A Roman engineer named Vitruvius wrote about these mixes in his book on architecture around the 1st century BCE. His notes helped later builders understand how Romans thought about mortar, lime, and volcanic sand. But the most famous Roman concrete isn't in a wall, it's in the sea. Roman harbor concrete has been studied because parts of it stayed solid in salt water for centuries, an environment that often damages modern reinforced concrete. Scientists found that Roman marine concrete can grow new minerals over time, including a crystal called aluminous tobermorite. In simple words, the material can slowly change into a tighter, rock-like structure as seawater moves through it. That's wild. But here comes the first "you think X, but Y" moment. You might think this means Roman concrete always heals itself and always gets stronger. Evidence is more careful than that. Different Roman sites used different local materials, and some techniques may not have been used everywhere. In January 2023, researchers reported a big clue. Many Roman concretes contain small white chunks called limeclasts. For years, people thought those chunks meant sloppy mixing. The new idea is the opposite. The chunks may have been part of the plan. When tiny cracks form and water gets in, those limeclasts can dissolve a bit and then reform minerals that help fill the crack. Think of it like a scab. It doesn't make the building immortal, but it can slow down damage. How did those limeclasts survive in the first place? One proposed answer is hot mixing. That means using quicklime in a way that creates heat during mixing, leaving behind reactive bits that can help later. And in December 2025, a new set of findings from Pompeii gave this idea a dramatic boost. Archaeologists found a construction site frozen in time by the 79 CE eruption of Mount Vesuvius, complete with materials that point to hot mixing methods. But don't miss the key phrase, "point to." Even the reporting notes that we still have questions about how common this was across the whole empire. This is science and archaeology working together, and it's still unfolding. So yes, Romans had smart chemistry, volcanic ash, limeclasts, mineral growth, but chemistry alone doesn't explain why a Roman dome can still sit over your head today. The next piece of the puzzle is shape.
Modern skyscrapers are often like very tall skeletons. Steel or reinforced concrete frames carry the load. The outer walls can be lighter, often glass. This saves weight and makes space, but it also means you must protect the skeleton from rust, fire, and water. Many famous Roman structures are the opposite. They are mass structures, thick walls, arches, and domes that push forces down and out into heavy supports. They don't rely on a hidden steel skeleton because they don't have one. Take the Pantheon. Its dome is about 43 meters wide, and the Romans made it lighter toward the top by changing the concrete mix, using lighter stones like pumice higher up. That's not just strength, that's smart weight control. Now notice what's missing: steel bars inside the concrete. Modern reinforced concrete uses rebar, steel rods, to handle pulling forces. But steel has a weakness. If water and salt get in, steel can corrode, expand, and crack the concrete around it. This is why you see chunks of concrete falling off old parking garages and bridges. The concrete didn't rot like wood. The steel inside changed, grew rust, and pushed outward. Romans mostly avoided that exact problem by building without steel reinforcement. They still had cracks and wear, but they did not have a hidden metal core that could slowly break the structure from within. So here's another "you think X, but Y" moment. You might think modern buildings should automatically last longer because modern science is better. But modern buildings also carry modern extras: plumbing, wiring, elevators, air systems, and tons of moving parts that age out fast. And that leads straight into the real secret reason. When engineers design a structure, they often talk about design working life. It's a planning number, how long the structure is intended to meet performance goals before major replacement or renewal is expected. In Eurocode guidance, common building structures are often planned around about 50 years, while some major bridges and monumental works are targeted longer. This doesn't mean a building must fall down in 50 years. It means the design assumptions, maintenance planning, and cost choices often aim for that kind of time horizon, because owners and cities plan in decades, not millennia. Now zoom out from engineering and look at real life. Data on commercial buildings in the United States shows the building stock is often decades old, with many built before 1980, and a median building age in 2012 of about 32 years. Buildings can last a long time, but many are also replaced as needs change. A 2025 study of about 15,000 demolished buildings in several US and European cities found an average lifetime around 71 years, with large variation. The big lesson is simple: demolition often happens before the end of a building's technical life. Why tear down something that could still stand? Because buildings don't die only from cracks. They die from obsolescence, being out of date for what people want: layout, tech, safety upgrades, or money. CTBUH, an organization focused on tall buildings, notes that reasons for demolition can include things like outdated elevators, crumbling facades, and hazardous materials like asbestos, along with changing demands. Sometimes renovation is possible. Sometimes owners choose a new tower instead. Now compare that to many Roman skyscrapers, meaning they're big public structures: baths, basilicas, temples, aqueducts. These were often state projects tied to prestige and public life. They were not built to flip for profit in 20 years. They were built to say, Rome is here to stay. That's the hidden constraint. Romans were willing to spend huge resources up front: stone, labor, time, because the goal was permanence. Modern developers often face the opposite pressure: build fast, build safe, build within budget, and make it pay back soon. In some ways, yes, Roman builders learned by experience how to mix local materials into durable concrete. Modern science is now explaining parts of that recipe, like lime clasts and mineral growth, with microscopes and chemistry. But in other ways, we know far more today. Modern skyscrapers must handle strong winds, earthquakes, fire rules, accessibility, and dense systems inside. Codes exist because people died when buildings failed. Safety is not optional. And modern concrete isn't bad. It can be extremely durable when it's designed right and maintained.
Many deterioration processes become more serious as concrete goes beyond a normal 50 to 100-year service life, which is why maintenance and durability design matter so much. So the fair comparison isn't Romans good, modern bad. The fair comparison is different goals create different buildings. If you build for speed, flexibility, and profit cycles, you get one kind of city. If you build for empire-level permanence, you get another. Here's the hopeful part. Engineers are studying Roman concrete to make modern concrete last longer and produce less carbon. If we can use more volcanic-like materials or design mixes that self-heal small cracks, we could cut repair costs and waste. But the bigger lesson may not be a recipe. It may be a decision. If we want buildings and bridges to last longer, we have to reward long life, better maintenance, better durability standards, and designs that can be upgraded instead of torn down. Because the secret reason Roman buildings outlast many modern towers is not only what they poured into their forms, it's what they poured into the idea of the building: time. They built like the future was watching. So next time you walk past a shining new high-rise, ask yourself a strange question. Not is it strong, it probably is. Ask, what was it built to be? A 30-year investment? A 100-year landmark? Or a 2,000-year message?